So in this video I'm going to run through the questions you need for quiz 12. This video is on CC11, which is the reactivity of metals. So revision from year 10, as well as some of the stuff on alcohols that we've been doing this year. Quite a bit of this I feel you can probably get from the mark scheme, even if you've forgotten it, but there's a few things I do want to go through. First one is question 24. These are about displacement reactions, which we did look at this year with the halogens, but we looked at them last year also with metals. So if you remember, we did them with halogens this year, and the rule was if the halogen by itself is more reactive than the halogen in the compound. So there's an example. The halogen by itself will take the place of the halogen in the compound, and you're going to end up with sodium chloride instead, and iodine. And each time you have a reaction, you're going to see some sort of color change. You can do exactly the same thing with metals. So down here they give you three metals. They say you've got copper, you've got magnesium, and you've got zinc, and you've got three different solutions: copper sulfate, magnesium sulfate, and zinc sulfate. And they want you to plan how you would work out which is the most reactive. So you're going to do displacement reactions, and what that will involve is you'll take copper and you'll put it in magnesium sulfate, and you'll put it in zinc sulfate. If copper is more reactive than magnesium, copper will take magnesium's place and you'll form copper sulfate, and magnesium will be left by itself. And when that reaction takes place, you will see a color change. Similarly down here, if copper is more reactive than zinc, copper will take zinc's place and you'll see a color change. So I need to test copper with magnesium sulfate and zinc sulfate. Similarly, I can take magnesium and I can put magnesium into the copper sulfate and into the zinc sulfate, and I can take the zinc and put it into the copper sulfate and into the magnesium sulfate. And each time you see a color change, it's because the metal that's by itself is more reactive than the metal in the compound, and it's able to take its place. Now, the reason I've just written these equations up here is that they're not actually needed in your answer. You're not asked about the specifics of these three metals. They just want to know in general, what would you need to do? So all you need to say on the mark scheme is that you take separate pieces of each metal and you put them into each of the salt solutions. So that's essentially what I've described here, but you just basically mix them together separately. So each metal will go into each salt, but separately. Any change in appearance or in color tells you that a reaction has taken place. And then the most reactive metal, which is magnesium by the way, is the metal with the most reaction. So with magnesium, I'm going to see a color change on both of these reactions, and that tells me magnesium is the most reactive. With copper, which is the least reactive, I won't see any color changes here, and that's how I know copper is the least reactive. But again, you're not asked for the specifics, you're just asked in general, how would you do this practical? The next question I want to talk through is this one here on redox. Again, this is something we came across in chapter 13, looking at an equation to see if oxidation and reduction have occurred. So luckily in this case they've written the ionic equation for you underneath. So they've gone through the actual equation and they've written it as an ionic equation, so you can see all the charges, and this is going to make it much easier to spot. But they're asking you to explain why it's described as redox. You need to know that the word redox means reduction and oxidation, and the first line on the mark scheme just says that it's a redox reaction because reduction and oxidation occur. So you get 1 mark for just saying reduction and oxidation occur, but then you need to show what's being oxidized and what is being reduced. So I'm going to do this writing half equations. I know some of you don't particularly like that, but it's the easiest way of picking up all of the marks without making any mistakes in words. So I've got two elements in my equation. I've got titanium and magnesium. I'm going to start with magnesium. And on the left hand side of the arrow, magnesium is just Mg, there's no charge, so I'm going to write Mg without any charge. On the right hand side of this arrow, Mg has a 2 plus charge, and I'm just going to copy that down, Mg with a 2 plus charge. And then I need to ask myself, how does magnesium end up with a positive charge? Does it lose electrons or does it gain electrons? Well, if I want it to have a positive charge, it must lose 2 electrons. So I write minus 2 electrons, now it has a 2 plus charge. And because magnesium is losing 2 electrons, I'm just going to write here that this is oxidation. and that will get me the mark. Now there is a big 2 in the equation. You can bring that down as well. You don't have to, but if you do bring the 2 down, if you're talking about 2 magnesiums, then in total you would need to lose 4 electrons to form 2 magnesium ions. So in this case, I think it's just easier not to bring down the balancing numbers, just to bring it down as is, and write your equation. For titanium, I'm going to do exactly the same. So on the left hand side, titanium has a 4+ charge. On the right hand side of the arrow, titanium has no charge at all. How is it going to go from having a 4+ charge to having no charge at all? Well, it's got a 4+ charge because it lost 4 electrons. If you give it those 4 electrons back again, it's not going to have that charge anymore. And I can say that this is reduction. Now, if you look in the mark scheme, if you wrote titanium is reduced, you are wrong. The titanium ion is reduced, and that word ion is in bold. If you don't write the word ion in your written answer, you don't get that mark. But by writing the half equation and showing the charge, I get my mark because I'm showing specifically it's the ion that is gaining the electron. So either write the half equation or remember to include the word ion in your answer. Over here, another one with titaniums. I've just worked out for you in case this wasn't clear. So titanium is a 4+ charge. Sulfate, they tell you, is 2-. To work out the formula, you cross the charges over. So the 2 is next to the titanium, the 4 is next to the sulfate. But the empirical formula is always the simplest whole number ratio, and I can divide across by 2. So if I divide across by 2, I get Ti and then SO4 2. You are not changing the sulfate, okay? The sulfate is a polyatomic ion, and that formula cannot be changed. You can just change the ratio of the titanium to the sulfate ions. The next one is another redox one. So again, explain in terms of electrons which particles have been oxidized and which particles have been reduced. I haven't written the ionic equation for you, so the first thing I'm going to go do is go through the elements and decide what charges they have. So if I start off here with zinc, zinc is an element, and when it's an element, it's got no charge at all. And I know zinc is an element because it's by itself and it's not bonded to anything. Then I come across here and I've got copper sulfate. Now again, you need to remember that sulfate is all one thing. SO4 is a polyatomic ion and it's got a -2 charge. And if sulfate has a -2 charge, then copper must have a +2 charge because the charges in ionic compounds must cancel out. On the other side, again, I've got sulfate, and the charge on sulfate is -2. And again, if sulfate is -2, zinc must be +2 because the charges have to cancel out. At the end, I've got copper. Copper is an element this time because it's not bonded to anything, meaning its charge is 0. Okay, so I need to use sulfate to work out the charges on copper and zinc because they're transition metals, so I can't use the periodic table. So now that I've assigned these charges, I need to see what's changing. And you can see the sulfate stays as -2 on both sides of the equation. That means it's not being oxidized and it's not being reduced. But zinc is going from 0 to +2, and copper is going from +2 to 0. So they're the two I'm going to focus on. And again, I'm going to write half equations. So I'm going to take zinc. On the left-hand side, I've got no charge on it, so I'm just going to write Zn. I'm going to draw my arrow. And on the right-hand side, I said zinc has a +2 charge. So I'm going to write zinc +2. And then in terms of electrons, what happens to zinc to end up with a +2 charge? Well, zinc loses 2 electrons to have that +2 charge. And then I can write here that this is an example of oxidation. And I'll just write because electrons are lost. And that's enough to pick up the 2 marks. I don't need to write anything else. Next thing I'm going to do is copper. And on the left hand side, I have said that copper has a +2 charge, and I have to include those charges when they're there. And on the right hand side, I've said copper has no charge at all, so I write it without any charge. So what happens to copper to go from a +2 charge to no charge at all? Well, it had a +2 charge because it had because it had lost 2 electrons. If I give it those 2 electrons back, it's not going to be charged anymore. And this is reduction because electrons are gained. Now again, if you're going to write this in words, you're going to have to say that copper ions are gaining electrons. If you just write copper, you're not going to get the marks. Therefore, again, I think the half equation is easier. It avoids you having to use words. Plus, in some cases, they'll ask you to write half equations, so it's a good idea to be able to do them. Actually, I skipped one question that I intended to go through. It asks you how you can get copper from copper oxide. If you look at copper's position on the reactivity series, okay, if I were to put carbon in here, and you need to know where carbon sits, carbon is in between aluminium and zinc. Because copper is less reactive than carbon, you can use carbon to extract copper from copper oxide. So essentially what you'd have here is you'd have your copper oxide, you've got your carbon, and because carbon is more reactive than copper, carbon will take copper's place, and you're going to end up with carbon dioxide, not just carbon oxide, and you'll end up with copper by itself. So they ask you to describe that. So if you're describing that in words, you have to heat these together. So you would heat carbon, so I'm just going to write here heat. You need to use heat to get these two to react. You would heat the carbon with the copper oxide, and the carbon will displace the copper, and you'll end up with pure copper. They give you a few other options on the mark scheme. They say that you can use hydrogen instead. That's because, again, if I look at the reactivity series, hydrogen is here, it is above copper, so instead of using carbon you could use copper, and in actual fact you can use anything that's more reactive than copper. So you could pick any of these metals and you would still get the marks. It's just that these metals are more expensive, whereas carbon is coal, it's cheaper and it's more accessible, which is why we use it. They also allow you to talk about electrolysis. Electrolysis isn't necessary here. Electrolysis is only necessary for the elements more reactive than carbon, but you could use electrolysis. However, at the moment the copper oxide is in solid form. For electrolysis to work, it needs to be liquid, so molten or aqueous, and what you would typically do is you would dissolve the copper oxide in some sort of acid, and once it was in solution, then you'd be able to do electrolysis on it. But I think all of those methods are more complicated. This is the method that we actually learn about. Carbon's more reactive than copper, therefore you can be used to displace copper from copper oxide. Right. Alright, now we're on to the organic chemistry. So they've drawn an alcohol here, and it says it can be dehydrated. If it's dehydrated, you are losing H2O, okay? The OH in H2O is going to come from this carbon here at the end. And you need to remember that the hydrogen for the H2O comes from the carbon next to this carbon, alright? So this carbon loses the OH, the carbon next to it loses a H. That loses OH, this one loses H, okay? So I'm going to redraw this with those things gone. So CH3, nothing's changed. CH2, nothing's changed. Here, I'm saying it loses a H, so I'm just going to write CH. And here, I'm saying it loses an OH, which means I'm left with a CH2. Okay, so all I've done is I removed hydrogen from that carbon, going from CH2 to CH. I've removed an OH, going from CH2OH to just CH2. Now if we look, I know it's harder when it's drawn like this, but if we look at how many bonds there are, this carbon has now only got 1, 2, 3 bonds. So it's bonded to hydrogen and it's bonded to the carbons on the left and right. And this carbon here also has only 3 bonds. So to give them 4, I'm going to have to put in a double bond there. Okay, you need to know that when you dehydrate an alcohol, you always form an alkene. The other product is just the water that you've lost, and when they ask you to name it, you have now made an alkene that has 4 carbons, therefore it's going to be buth. I know it's an alkene, so it ends in ene, but where is that double bond? I number to give the lowest possible number to the double bond, which means it's buth 1-ene. I'm numbering from right to left, and then this product is obviously water. The next one, if you are going from ethanol to ethanoic acid, you're adding an extra oxygen, therefore it's oxidation. That you can get from the mark scheme. This next one, I'm not going to write out the whole answer, but I've asked you to learn what it is to be a homologous series, and you learn that they have to have the same general formula. Now, even if you can't spot what the general formula is, it doesn't matter. They're telling you they're in the same homologous series. Say they all have the same general formula. Successive members should differ by a CH2. They've put the members in a random order, okay, but ethanoic acid has 2 carbons, propanoic has 3, then buthanoic 4, pentanoic 5, and hexanoic 6. So going this way, that's the successive members of the family, and you can see they all differ by CH2. Again, even if you don't see it, just say it. They all differ, successive members differ by a CH2. You should also see a trend in physical properties, and you do when you look at them in order, okay? So the density of ethanoic acid is 1.05, propanoic is 0.99, buthanoic 0.96, pentanoic 0.94, and hexanoic 0.93. Those densities are decreasing as you go along the group, and if you look at the boiling points in the right order, 118, 141, 164, 186, 205, the boiling points are increasing. And then your other property is chemical properties. So these two will both be physical, density and boiling point. These are both physical properties. So you can say they show a general trend in physical properties. Densities are decreasing and boiling points are increasing. And then you can say they show similar chemical properties because they're both reacting with alcohol. They're all reacting with alcohols. They're all reacting with sodium hydroxide. So there's lots and lots that you can say to get 6 marks there. But make sure you are using the data, so refer back to the trends in density and boiling point, refer back to the specific reactions you've been given. Again, another dehydration question, okay? It's drawn a little bit differently for you, but again, this carbon here is going to lose the OH. The carbon next to it is going to lose the hydrogen. And when that is happening, if I, again, you don't need to draw it this time, but I'll just draw it out. I've got a CH3 at the end. That carbon is now just a CH. This carbon is now a CH2, so it's a little bit easier to see. For all the carbons to have 4 bonds, you're going to be putting a double bond in there, and you are going to be drawing propene. Now there's no need for a number in this case, because rather I'm numbering from right to left or left to right. I'm going to end up with propene, prop1ene. If I put the double bond there, I would just number from left to right. So it's just going to be propene. There's no need for a number, but if you wrote prop1ene, that would be fine. Give the formula of the functional group formed. If you oxidize an alcohol, you will form a carboxylic acid, and the formula of the carboxylic acid functional group is COOH. What happens to propanol when it forms Y? Again, you're going from an alcohol to an alkene. In this case, you can see by the general formula C3H6, double the number of hydrogens. It's an alkene. How do I go from an alcohol to an alkene? Well, it's being dehydrated. You're losing water. Compound Y can also be formed. Explain how bromine water can be used to distinguish between X and Y. So X is an alkane. I know that because there's double the number of hydrogens plus 2, and this is an alkene, and they want to know how they can use bromine water to distinguish between alkanes and alkenes. Well, bromine water will react with alkenes, and you will see a colour change from orange to colourless. Bromine water will not react with alkanes, so you're not going to see a colour change. And that's all you have to describe. So we saw that a week or 2 ago when we looked at addition reactions of alkenes. This should be alright. And then this last one here, compound Z is an acid and turns litmus and universal indicator red. Any other experiment that shows it's an acid. So you can't use universal and you can't use litmus. You could use a pH meter, okay, to show that it's got a pH less than 7. You could react it with a carbonate base. You would see bubbles. It's an acid, so it'll react with a carbonate base. You can react it with a metal. You'll see bubbles because hydrogen will be produced. So basically any reaction that you can think of that you've studied with an acid, you can say that here. And you can't use litmus or universal, but you could use a pH meter to measure the pH and show that it's less than 7. And that is it.